Hello, Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG. And today we have another episode of Ask Dave. The question comes from Bob, K6ECM. And he says, I see what appears to be a frequency hopping transmitter running left to right across my SDR spectrum display, creating a diagonal dotted line in the waterfall. Any ideas about the source and its use? The signal is quite strong. Well, I just captured one for you using my ICOM 7300 here, and the IF output of this is attached to my little SDR Play Duo right here, which is attached to the computer and has created this screen. And what we're going to do is take a look at one of these signals and see what it's about. What you're looking at is an ionospheric sounder. Usually they'll go a long ways and just go right on through, and you hear sort of a whip like this, from low frequency to high frequency. And that's the way many of them work. What they're doing is they're sounding, meaning sending a radar wave up to the ionosphere and capturing the reflections. And from this they can build an ionogram, which is a picture of what the ionosphere is looking like at any given time. And it'll show the different layers and so on. You can tell the distance to a layer by determining the amount of time it took for a particular signal to reflect. Oftentimes you will get multiple reflections. It'll reflect off, say, the E layer, and then the F1, and then the F2 layers, okay? And you can learn a lot about this. So you're looking at the ionosphere. Now, they don't really care that they're making a minor little annoyance in your ham radio conversation, or actually anybody's conversation for that point, because they're in the passband so quickly, in and out, just like that. But if you look at it on a waterfall, you can see the thing going across. So what I'm going to do right now is do a little bit of drawing on this particular shot that I got, and we'll be able to follow some of the dots. This one right here seems to be homing around a certain frequency. Let's look at this screenshot that I got of the 20-meter spectrum one afternoon. I had the tuner, which you can see up over in this area, at 14258, but you can see the whole band. This is the spectrum up here, and you know, it's neat to see the spectrum, but more people are interested in the waterfall. This dimension right here is time. The current thing that the receiver is getting is here, and then it ages down until it goes off. Across is frequency. So a signal that is on a single frequency will be shown as a vertical line. These are all single sideband signals over here. All this is pretty much Morse code. Right in here we get our FT8 and related modes. Okay, so they're really going to town in there. Now, this is what brought the question up. See that diagonal line? Now, the diagonal line means it's changing frequency, okay, in this case going up, and in this direction, this is older stuff to the newest stuff is here, is the one closest to the top. So it goes up in frequency. If you look really carefully, you can see it does not hit every frequency. There are little gaps in between, but not so small that when they go across a single sideband signal, you'll likely hear this. Now, the people who do this don't care about interfering with other people, because they really don't. It's just a momentary blip on the bands. Now, if you're doing RIDI or something like that, which would be in this area, you could possibly get a character that is switched. FT8 is not going to be affected, because even if it flips a bit or two, you're still going to get through because of the forward error correction capabilities. But this right here is an ionospheric sounder, and it's like a radar that looks straight up. They call them ionosones, and what comes out of them they call ionograms. This is the output of one of these ionosons. And the software here is called Digisonde, but this comes out of an ionospheric sounder. The scale here is megahertz from 1 to 10. Okay, and this is the height, I presume in kilometers, because everybody pretty much assumes in the scientific arena that things are in metric. Okay, so what happens when it hits something, it can characterize it and tell you there's an ionospheric layer right here. Now note that 100 kilometers is generally considered the boundary between the atmosphere and space. Well, that's way down here. And yet the ionosphere is actually part of the atmosphere. The International Space Station is right up in here. Okay, and you get other satellites up here and so on. There is a very small amount of atmosphere here. I mean, vanishingly small, but not so small that it doesn't slow the space station down. It does. And so every so often they have to fire rockets to boost the space station back up. And that is true of all low Earth orbit satellites. This is annotated and comes from Wikipedia. Okay, excellent annotation. So these are the transmitted frequencies. You see how it zips up. Now the one that we showed earlier was on 20 meters, so that would be over here. This black line tells you the electron number density versus true height. Okay, the red points are the locus of received ordinary frequencies and corresponding virtual ranges. The green ones are extraordinary. So these are the O waves. These are the X waves. And yes, the ionosphere does treat them differently, as I've said in a video or two. Okay, so the light blue indicates ionospheric reflections from the northeast sector. These are second time around or double hop. Now what that means is you transmit here, it continues going up and hits this, or it hits this, comes back to the ground, comes up and hits it again, and the ground thinks it's way up here. Okay, so you've got ordinary, extraordinary, and this will tell you down here what the maximum usable frequency is at different ranges. See, this is straight up, but the MUF, or maximum usable frequency, for 100 miles this way, is 5.5 megahertz, because you can see it just gets right in there, it stays there. But as you hit it at a slant angle, for a long hop, you can use up to 17 megahertz, okay? So this is for an oblique propagation line. Oblique means at an angle rather than straight up, okay? The black line is scaled by the Digisonde computer, plasma frequency versus virtual height, and it tells you all these things. Somebody who's really, really, really good at propagation can sit here and read this chart for hours. But this shows what an ionogram actually looks like. You can get these online, by the way. Okay, so we've taken a look at the kind of signal tracks made by an ionospheric sounder. You'll see them actually fairly frequently. You'll just hear them as a blip. Now, the reason that they can do this on HF, they will interfere with somebody else's transmission, is because HF is considered a noisy channel, and all of the digital protocols in serious use across HF have the ability to ignore this, go around it, fix for it, and so on. Some of our legacy modes, like RIDI, it's possible it could cause a one-letter change, and so you'll get an error in there. With PSK32, the system may or may not create an error. The PSK32 is more robust than it may seem. Not see that. And of course on voice it's no big deal. You just hear the little bleep and then that's it. Who does the ionospheric sounding? Mostly by universities, and they share this data with the government lead agency for this being NOAA, the National Oceanic and Atmospheric Administration. They're the Weather Bureau these days. And they do a lot of this. A lot of universities do this as a part of their research. Now, are they spread spectrum? No, they're not. Each individual dot is on a given frequency, and they go up from there. Spread spectrum would look very different. I should do a video on spread spectrum. It's not something you can do on HF legally. It has to be at 222 megahertz or above. You can experiment with spread spectrum, which is very, very interesting mode. There are quite a number of ways to do it. This is not one of them. So there you have it. You can see the thing on the band spread that I had here. The normal ones just go all the way up like this. They're going up in frequency, and the reason they go at a slant is because the waterfall is moving down. So a signal that changes frequency will show up as a slant because the waterfall is moving down. Hope that answers your question. Thank you for a question. That was an interesting one. And until we next meet, 73.